Welcome back to another episode of Space Nuts. I am your host for this season, Heidi Campo, and joining us is Professor Fred Watson, astronomer at large.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Fred, did you know that today is World UFO Day?
Oh, no, I didn't. I've got a feeling I saw something about that and then it moved on.
How do you know? So I'm trying to fill in for our normal host, Andrew Dunkley, and he loves his dad jokes. So I figured I'd need to bump up the dad jokes. So, Fred, how do you know if you are talking to an extraterrestrial?
Because their lips don't move.
Well, you need to ask them probing questions.
I love that. Yes, I like that very much.
It was not original. My Alexa told me that whole spiel this morning. I thought that was too good not to share with you guys.
Yeah, it's a good one. Yeah. It's a very probing answer as well.
Well, how are you today? Are you excited?
Well, look, I go through my life in a state of permanent excitement, Heidi. And who wouldn't be when we're mixed up with all this fabulous news coming from space, astronomy, physics, biology? We're being bombarded by all these marvelous discoveries. And that certainly, for me, is very exciting. And the annoying thing for me is that I'm at the sort of end of my career that means that a lot of the things I want to know the answers to may be beyond my horizon.
Man.
And that's really irritating. But that's okay. I mean, I'm thinking of things like, and this might be beyond many people's horizon. For example, the plans to build a new future circular collider, as it's called, by the CERN, the Nuclear Research Center on the French-Swiss border. They're planning this machine, which will switch on in 2070. And, we're going to discover wonderful things from it. But 2070 is beyond many people's horizon, certainly beyond mine.
Yeah, there's some existentialism in the first 3 minutes of the episode today.
Yeah, there you go. So yes, that's right. So for all you space nuts out there, don't worry. You'll all hear the answers to many of the questions that you want to know about, like dark matter, dark energy. Is there life elsewhere? All these questions are probably within your horizon, but maybe not mine.
Maybe one of these days. I know we had some kids come in with some questions on some of the Q&A episodes. Maybe one day when they're the hosts, these things will be discovered.
Exactly, that's right. That's the thing to look forward to. It's existential stuff, but it's good news stuff as well, because, science is one of those things that just keeps on moving and we keep on learning new things, and who knows what we might discover that will transform our understanding of the universe. I think that's the end of the show, isn't it, today, Heidi? I think we've covered everything there.
Oh, well, today is a great one. And here's my segue. We're going to just jump right into introducing all of our articles. We have history, we have mystery, and we have discovery. We are really covering the full spectrum of space science today. And our history article today is touching on basically a James Webb discovery of how the Milky Way was kind of formed. Is that about right, Fred?
Yep. Right on the money there, Heidi. And this is actually a topic that's close to my heart because I've been involved with research very like this. So what the Webb telescope is doing is looking at what we call cosmic archaeology, which is trying to understand basically the evolution of galaxies, the detailed evolution of galaxies. But it relates to something that has been very actively pursued in the last 20 years or so, a topic that we call galactic archaeology. And that's understanding how our own galaxy came to be put together. And that topic has led to some quite significant discoveries. The people I've worked with have made some of these discoveries. We've been working on a project called Galah. Galah is an Australian bird, a very well-known species of Australian bird, Galah. Galah stands for Galactic Archaeology with Hermes, being the instrument that we used to do this. So I was very much on the observational side of this project, but worked with people who discovered some of the fundamental properties of our galaxy. And that relates directly to the story that we've got coming from the James Webb Telescope, because one of the discoveries that my colleagues made was that the disk of our galaxy, and remember, our galaxy is this flattened spiral of stars and gas and dust and dark matter, which it basically is disc-shaped. And we see that when we see the Milky Way. We're looking through the thickness of the disk. We've known for a long time, more than 100 years, that there is another component to the galaxy, and that's what we call the halo. This is a spherical region of stars and what we call globular clusters, these very dense clusters of stars that surrounds the disk of the galaxy. But the people I worked with made a discovery that there is another component, and that is that the disk is not just a single item. It has two parts to it, which maybe not surprisingly are called the thin disk and the thick disk, because one's thin and one's thick, and they're two different sort of populations of stars. So the thin disk really is what we see when we look at the Milky Way, but there is a more rarefied population of stars that make up a thicker disk, and they've got different dynamical characteristics. That's to say, they move in different ways. So that's the segue to this story from the James Webb Telescope, because people are now looking at other galaxies beyond our own to see if the thin and thick disks can be detected. I mean, it's taken us, centuries, I guess, to work out that the disk of our galaxy was in two components. Let's now move outwards and look at other galaxies to see whether they are the same, and to see how that informs our own understanding of the evolution of our own galaxy. So the team of astronomers, one of whom was based here in Australia, I'm glad to say, and that's actually the team leader. That's again carrying on this tradition of Australian involvement with the idea of thin and thick disks. So they've looked at 100 galaxies up to 11 billion years ago. So we're talking now about very distant galaxies in the early universe, and basically look to see how the thin and the thick disks appear in those galaxies. In particular, the question they want to ask is, when you've got a galaxy forming and evolving, what is the point at which that structure that we have in our own galaxy, that dual disk structure, what's the point at which that forms? And so what they've done is they've chosen galaxies, and this is kind of what you'd expect them to do. They've chosen galaxies that we see edge on. And so that means that you're looking directly at the disk itself. It's edge on to you rather than face on. And that means that you've got a good chance of seeing the stars in the thick disk and the thin disk separated. And indeed, that's what they have found. And this is actually world-leading research. It's the first time that astronomers have studied these two populations of stars in galaxies in the early universe. So the bottom line of this story is that it looks as though, from the observations that have now been made of these 100 galaxies, it looks as though the thick disk forms first. So what you get initially is the thick disk, and then the thin disk within it forms later on. And so that's new knowledge. That's something that we didn't appreciate before. It's actually a very, very fine piece of research that feeds directly into our understanding of our own galaxy, taking information from distant galaxies in the early universe. I was full of admiration for it.
That's amazing. So why do they think that is? With the thicker disk that they think is the more mature one, are they seeing the clusters in a more ununiform spin then. So it seems like as the I don't know as the disks get more mature, the clusters get more sporadic.
Yeah, that's right. It's the stars themselves that define how these disks appear. And I think your point is right, though, because what we call the kinematics of the thick disk in our own galaxy, that's the way stars move in it. It's a lot more disorganized than the kinematics of the thin disk. The thin disk has very, very well-behaved star motions in it. For example, the sun is in orbit around the galactic center. It's a very neat and tidy orbit. It takes about 200 million years to go around once. And all the stars in our neighborhood are doing the same sort of thing. But the thin disk is less well organized. It's got much higher velocities outside the plane of the disk. So there's a sort of vertical component of the velocity of stars in the thick disks as well. And so you're right. It looks as though that older disk, being the thick disk being the first thing to form, stars in it eventually collapse towards a thin disk in response to the galactic pull of the whole galaxy. And perhaps an analog with this is the rings of Saturn, which are a very, very thin disk of material. You probably know the rings of Saturn are about 250,000 kilometers in diameter and less than 100 meters thick. 100 meters thick. So it's a blade of material in space. And that is because of the gravitational forces that act on it from the planet Saturn itself. And so it looks as though something perhaps analogous to that happens in our galaxy, that you eventually get the stars in the disk shepherded into this quite thin region, leaving behind remnants of perhaps an earlier phase, which is what we see as the thick disk.
So the opposite of most people, when we age, we tend to get a little bit thicker.
Nicely done. Very nicely
especially
put,
around
Heidi.
the middle.
Well,
oh
yes,
my.
that's right.
Well, we can't all be as beautiful as Saturn with its beautiful disks.
Let's take a break from the show to tell you about our sponsor, NordVPN. And we're very proud to have partnered with NordVPN so that we can get you more secure online, no matter what you do, where you are, or how you do it. Now, if you sign up for a 2-year NordVPN plan using the code word SpaceNuts, you'll receive 4 extra months absolutely free. That's 28 months of top-tier VPN protection at a fraction of the cost. With NordVPN, what you get is access to over 7,700 servers worldwide, ultra-fast connections, advanced features like Threat Protection Pro and MeshNet, and secure usage for up to 10 devices simultaneously. So you're pretty well covered, you have to admit. Now, this is a great opportunity, and if you'd like to take advantage of it, visit nordvpn.com/spacenuts to claim your exclusive offer today. And remember, with NordVPN's 30-day money-back guarantee, it's risk-free. It's a great investment, a small price to pay for your online security and privacy. Stay secure, stay connected, and keep exploring the cosmos with confidence. nordvpn.com/spacenuts, nordvpn.com/spacenuts, and don't forget the code word SpaceNuts at the checkout. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
But this next story is a mystery, and that's kind of fun and exciting. So, we just talked about our galaxy forming, but this next one is a little bit less straightforward than what you just explained. And I'm really excited to hear what you have to say, because you have such a great way of taking something complicated and making it make sense to us. But tell us about this, the surprise in the desert.
Well, yeah, so, and it's, again, this is relatively close to home. This is research that's being done here in Australia. And I think we've talked about it before, Heidi. A facility called the Square Kilometre Array Observatory, SKAO, is an international project. I think it's got 7, maybe 8 nations involved in it now, with facilities in Australia, in South Africa, and in the UK, and the UK is just where the headquarters is. So our telescopes here in Australia, there is the square kilometre array itself is being built. It will probably see fully first light, first radio signals in something like 3 to 4 years. But there is what's called a pathfinder, and it rejoices in this marvellous name of ASCAP, the Australian Square Kilometre Array Pathfinder. And that's used very effectively for finding many different sorts of objects in space. It has about 30 dishes in the Western Desert of Australia. And in particular, it's been really good
30.
At finding these things called fast radio bursts, which my colleagues in the radio broadcasting business tell me should be pronounced fast radio bursts because they're very fast.
I don't know why that was so funny to me.
Anyway, well, it's a bad name because really they're short radio bursts. They're, they're something like a millisecond long, and they're flashes of radiation, which have now been recorded for something like a couple of decades. And so they've been very well studied. And we think they come from what are called magnetars. These are neutron stars, highly collapsed stars, which have very strong magnetic fields, and you get flares on these stars. That's what we think fast radio bursts are caused by. But in making those measurements, this team of astronomers actually came across something that was a burst of radiation, very bright, a bit like a fast radio burst, but rather than being a thousandth of a second long or thereabouts, this was a few billionths of a second long. It was incredibly brief. So the pulse that they measured lasted for 30 nanoseconds, 30 billionths of a second. And that's a mystery. We have never seen anything like this before. So they were puzzled. It took them a year to try and work out what it is that we think we're seeing. And first of all, they had some hints that it might be quite close by, because in the radio telescope world, there's a phenomenon called dispersion. If you have a pulse of radiation, the higher frequencies get to you before the lower frequencies. That's the phenomenon of dispersion. And so that is something that you look for as a kind of indicator of distance. Now, this particular 30 nanosecond pulse didn't show that dispersion phenomenon. And that tells you that it's coming from relatively nearby rather than deep in the universe, unlike the other things. And in fact, they could also see that it was out of focus. It had blurriness in the image. And so that let them put an estimate of distance on it. And rather than it being several billion light years away, like most of the fast radio bursts are, the distance they got for this was 4,500 kilometers. What's that? That's about 3,000 miles. So that's rather nearby, which tells you it is probably coming from a satellite. And so they worked out from the direction that they'd seen it in what satellite it might be, and they identified one. And it's a satellite called Relay 2 that was launched in 1964, and it was one of the first telecommunication satellites. Now, by 1967, the whole thing had switched off. It was just a defunct piece of space junk. So this satellite, Relay 2, has not done anything for, 60 years, nearly 60 years. And so it's a real puzzle as to why a dead satellite should suddenly produce a flash of radiation that's a billionth of a second or 30 billionths of a second long, and be incredibly bright. And I think the only thing that the team has been able to come up with, and they're saying they think this is the most likely cause, is an electrostatic discharge. And we're all familiar with those. When you've got very dry weather Sometimes your clothes, as you take them off, if you've got synthetic fabrics in your clothes, they rub against your skin. They cause a buildup of static electricity, and you get a little spark. Once in a while, you can actually see those if you're in a dark room. Take your jacket or your shirt off, and you suddenly see flashes all around you.
Here's a cute little story about static electricity. Every morning, my dog sleeps in the bed with me, and every morning he sleeps down by my feet. Every morning he kind of scoots slowly across the bed, and he doesn't understand physics. He doesn't understand that it's the slow scoot towards me that's building up that static electricity. And he goes and he gives me a little kiss on the cheek every morning, and he always gets that shock right on his nose. And so he's developed the habit of scooting slower and slower. And the poor little guy just keeps building up more static electricity every single time.
That's right.
So I try and touch him on his shoulder or something before he gets to me so it doesn't get him on his nose. But yeah, so they're calling us the zombie craft. And it was the United States
it was, yes.
Satellite.
Yeah, that's right. And so the thing they think is the most likely is one of these an electrostatic discharge, just like your dog's nose, but causing a flash of radio radiation. But they say the problem with that idea is that usually electrostatic discharges relative to this one are quite slow. They last thousands of times longer than the 30 nanoseconds of this signal. So they postulate a second hypothesis, which is a strike by a micrometeoroid, a tiny piece of something, which could produce a flash of radio waves. But they say that's got very low probability. So the bottom line is we don't actually know. We simply don't know what this signal is. And maybe we will find a few more insights, but that's the story from this team that's hit the news. Even though they're doing fabulous work on fast radio bursts, the thing that hits the headlines is the mystery signal.
It is quite the mystery, and that is an interesting one. I'm going to be scratching my head about that for a little while.
Time to take a break from the show to tell you about our sponsor, Incogni, INCOGNI. I'll give you a special URL shortly so you can get it 60% off Incogni as a Space Nuts listener. And if you're tired of your personal information being spread across the internet and getting hammered by all these spam emails and spam texts and spam phone calls, then Incogni is the answer. It's a privacy tool that scrubs your sensitive data from over 180 data broker sites automatically. Whether it's your phone number, your home address, your browsing habits, your email address, whatever personal information is online is cannon fodder for these people. Incogni uses legal rights like GDPR and CCPA to get your data removed. You sign up and Incogni does the rest, sending removal requests and tracking progress on your dashboard. It's fast, it's secure, it comes with a 30-day money-back guarantee. It's an inexpensive way of getting yourself cleaned up so that you don't get spammed. And who knows what else is happening to your data online. So go to incogni.com/spacenuts and use the code spacenuts for 60% off right now. Incogni.com/spacenuts, 60% off. And don't forget the code word spacenuts at the checkout. Incogni.com/spacenuts. Now back to the show.
0G and I feel fine.
Space Nuts.
I'm glad that our last story gives us a little bit of closure with a new alloy that was discovered, a new alloy it's needed for an exoplanet discovery.
This is it's a really interesting story because, why should something that seems to be metallurgy find its way into space and astronomy news headlines? And the answer is that it's got a definite application in our hunt for exoplanets, for planets around other stars, and not just hunting for them, but to try and characterize them, to try and learn more about them. So the curious thing about this alloy is that it has a negative coefficient of thermal expansion. And so what that means is, as we know, when things get hot, they tend to get bigger. It's just like when they age. A piece of metal, if you heat it up, it gets bigger, and the rate at which it gets bigger with temperature is something we call the expansion coefficient, the thermal expansion coefficient, basic physics. There are a few materials, and one of them is very well known to astronomers, a few materials that don't expand or contract with temperature. They don't do anything. And one of them is a glass ceramic material, which was developed in the 1970s. There are two versions of it. One is called Servit, that was made by Owens, Illinois in the United States. And the other, I can't remember its name, but it's made by the Schott Glass Company in Europe. These are effectively what looks like a piece of brown glass, but it's a mixture. It's got the properties of both glass and a ceramic, and it has a zero expansion coefficient. So as the temperature changes, if you make a telescope mirror out of this, which has a surface accurate to a few billionths of a meter, if you make a mirror out of this, as the temperature changes, it doesn't alter its shape. And that is why most of the mirrors of big telescopes in the world today are made from this material, including the one I used to be astronomer in charge of at Siding Spring Observatory. But this new material, this new alloy, has the opposite characteristic. When you heat it up, it contracts. And that's very much, it's very different from what we expect to find with metals. But what it does is, because it's so different from normal metals, it gives you the possibility of building structures that have some of this new alloy in them, which will contract with temperature. It's called Alvar Alloy 30, by the way, to give it a name. It's if you can combine that with metals that have the normal thermal expansion characteristic, then one can compensate for the other, and they can essentially cancel out any form of temperature distortion that you might get. As the temperature changes, your structure is built in such a way that it doesn't change its shape, because the two different coefficients cancel out. And that's important in one specific field which has been identified. And this actually is appropriate for both space telescopes and ground-based telescopes. When you're looking for planets around other stars, what you need is absolute stability in the instrument. Because the measurements you're trying to make, whether they're what we call the Doppler wobble technique, which is where the motion of a planet around the star pulls the star slightly one way and then the other as it goes round, and we see the star exhibiting that backwards and forwards motion, which can be measured. Whether it's that, or whether you're looking for a direct image of a planet going around its parent star, all of these need instruments that are utterly stable over long periods of time. The way you normally compensate for this, the way we've done this in the past, is to have very sensitive calibration mechanisms, so that you can, as you take your observations, you also take calibration measurements that tell you whether that your instrument is changing its shape, and that lets you then compensate for it. But with this new alloy, you wouldn't need to do that. If you built your structures with normal metal and this alloy 30, then you could make structures that really need very little calibration. And that means that you can make these high precision measurements with the minimum of fuss. And in particular, if you're talking about a space telescope, which is not particularly hands-on because it's up there in orbit, then you've got a system that will withstand the temperature variations that you experience in space as you go in and out of the Earth's shadow, and remain stable. So I think this is quite an interesting discovery, just for its own sake. Whoever would have thought of a metal that shrinks as it gets hotter? I certainly wouldn't. And then, but it gives a really interesting astronomical application.
Yeah, I was just looking here too. It sounds very similar to another metal that I've been researching a lot lately. And I don't know if we're talking about the same thing, but a smart, shape memory alloy. Are you
Oh,
familiar with shape
yes.
memory alloy?
Yeah, yeah.
So these are different then.
They are, yes, but the shape memory alloys, that's a really interesting thing too, because it remembers that, you deflect it and it has memory of how it's been deflected. They may be made of similar materials. Some of these alloys are quite complex chemical entities. They've got unusual chemical reactions to make them, and maybe there might well be connections between the shape memory alloy and the negative expansion alloy, probably all made by the same company somewhere down the track.
Yeah, well, it's so interesting because it's like the shape memory alloys or SMAs are also really being used a lot in space with,
Yes.
well, they're not being used in space yet, but there's hopes to have kind of smart textile spacesuit design. And I
Yeah.
know that MIT's been working on those spacesuit fabrics a lot, but they've kind of hit a little bit of a roadblock because of the amps required to make it work. It is unsafe to have around humans. It's
Okay.
the
Yeah.
amps would be too high and would stop a human heart. So they're still looking at it, and maybe we're on the cusp of having something really cool. I think of Back to the Future, I think is Back to the Future 2, where he has the shirt and the boots that the fabric absorbs up to be the right size for him.
That's exactly what these things are going to do, as far as I understand it. The shape memory fabrics, I didn't know that they were currently too dangerous to wear. That's a bit of a it's perhaps not an undesirable aspect of these fabrics, that if they have currents that are too high for the human heart to withstand. But yeah, obviously the research is going in the right direction with that. Yeah, it's really interesting stuff. And as
It
you
really
say,
is exciting.
yeah,
Yeah.
yeah.
And even, maybe I always say this. I say this, I think maybe every episode or every other episode, it could be the people listening who are the ones working on this stuff and making those breakthroughs. So, and maybe this is the episode that connected those two dots for
That's
someone
right.
out there to be the one who makes that discovery. You heard it here, folks, on Space Nuts.
That's one of the reasons why we do it. Who knows who's listening and might make a brilliant discovery. Space Nuts
Excellent.
is to blame.
Space Nuts, yeah. You can give us a little note on the acknowledgments on your manuscript.
That's right. Yeah, absolutely.
Well, thank you so much, Fred. This has been a lovely conversation. I really enjoyed chatting with you today, and I will look forward to talking to you again in our Q&A episode next.
Sounds great. Thanks, Heidi.
Hello, Heidi. Hello, Fred. And hello, Hugh in the studio. Andrew here from the Crown Princess. We're over a month now into our world cruise. And since I spoke to you last, we have been super busy. We got around the Horn of Africa eventually, and we stopped in Cape Town. Weather wasn't great, but it did clear up, and we had a fabulous 2 days there. And we went out on a safari, which was a couple of hours drive out of Cape Town, and saw some fabulous scenes, beautiful animals, giraffe. We saw a baby rhino that was apparently born that day, trailing along behind its mum, so it got its legs sorted out. And we saw buffalo, we saw lions, and we got up close with them. They actually came up to our vehicle, beautiful creatures. Didn't feel too apprehensive about them being, face to face, but it was terrific. And plenty of other things. And then the next day we went to a colony of penguins at a place called Boulders Beach. They're the African penguins. They're highly endangered, and they were so cute, and a lot of babies there as well. So got to see all that, and Cape Town was fabulous. And by the time we were leaving and the ship was pulling out, the skies cleared, and we got to see the famous Table Mountain. So, just a terrific time. And then 2 days sail later, we were in Namibia. Now, we were told by the people on the ship not to expect much, that Namibia, Walvis Bay particularly, was a bit of a backwater, and it wouldn't be the greatest stop to make, but we would like to disagree with the cruise staff, because we had a fabulous time. We went out four-wheel driving on the sand dunes that Namibia is famous for. We went out on Walvis Bay and saw more living creatures than we've seen anywhere. Colonies of thousands of seals, fur seals, who came swimming up to the boat to say, "Hello, what's all this then?" Fred would understand that accent, and one of them actually jumped in the boat and obviously was used to being around people. We got visited by a pelican who jumped on board. We got visited by a seagull who jumped on board. We visited the salt pans. Salt is a major export of Namibia, and we were driving along with sand dunes on the left and the Atlantic Ocean on the right, and only a track to separate them, and it was just amazing, just an incredible country, such lovely people, and I would highly recommend Walvis Bay and Namibia to everybody. They're just about to make an announcement, so that'll probably interrupt me, but I won't stop because I'm nearly finished. We are now heading northwest. Our next stop is Tenerife, and I believe we just past the day that is where the Earth is the furthest from the sun. So that's my little astronomical analogy for you today. And I'm aphelion, is that what it's called? I think I'm right. Fred will correct me. But anyway, that's where we're up to. Tenerife, next stop, and I'll report in again real soon. Hope everyone's doing well. I'll try and post some pictures on the Facebook page. I just keep forgetting, and the internet here is clunky at best, but we're managing. All right, talk to you all soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.